In this video, we're going over an area of physics known as kinematics, and we're starting with the simplest case of kinematics, which is in one dimension. Kinematics is the study of motion without considering any forces. This means we want to describe motion, but without giving any attention to the forces that cause that motion. We will describe the motion of objects using both vector and scalar quantities. These are displacement, distance, velocity, speed, acceleration, and time. We'll begin by discussing displacement and distance, which are similar but not exactly the same. Displacement is the change in an object's position, and like position, the units of displacement is meters since it has a dimension of length. We typically describe an object's position with a coordinate on a coordinate system. The position represents some distance from the origin of that coordinate system. We're interested in the motion of an object, and if an object is in motion, its position must be changing. This is a common theme in physics. We're often more interested in the change of a quantity than the actual value of that quantity at any given time. In fact, we have a special notation for the change in a quantity. We write this with a Greek delta that looks like a triangle. For example, if our position changes from the point x1 to the point x2, we can write this as delta x, which is the displacement. Anytime we see this delta, mathematically we should think final minus initial. In this case, final is the ending position, or position x2, and initial is the starting position, or x1. The order matters because displacement is a vector, and changing the order will lead to the displacement pointing in the opposite direction. We could also write this as xf minus xi, where f and I stand for final and initial. And a final way to write this would be x minus x naught, naught meaning 0. The 0 here refers to the position when time is 0, which is when we usually start the imaginary clock we use to describe motion. Then x is just the position at some later time, and we still often call this the final position. You may see any of these notations, and they all mean the same thing, just with a different labeling of subscripts. Sometimes, one notation may feel more appropriate than another, but in the end, subscripts are always just a tool that we use for organizing quantities to describe physical scenarios and solve problems. So to some degree, you can use whatever notation you want, just make sure you're able to clearly communicate it. Now let's look at distance. Distance is the total length traveled, and we often write it as d. The units are again meters because it is a type of length. Distance is a scalar, which means it has no direction, and in this case it's always going to be positive. In contrast, displacement can be negative. Let's look at an example to highlight the difference between these two. Say an object moves along the x-axis from position 20 meters to the right of the origin to a position 100 meters to the right of the origin. The displacement is the final position minus the initial position, or 100 meters minus 20 meters. This gives a positive 80 meters. And obviously the distance traveled from 20 to 100 meters is also just 80 meters. So in this case, the magnitude of the displacement is the same as the distance. But in general, this is not true. Let's look at another example where the direction changes. Say the object moves from x equals 20 meters to x equals 100 meters, and then stops, turns around, and moves back to the original position at x equals 20 meters. Well, the object has moved through twice the total distance it went through before, since it did the first trip back again, but the displacement will be given by 20 meters minus 20 meters, since the final position is the same as the initial position, and the displacement is therefore 0. So now we have a case where the distance and displacement are very different, but that's okay because they can be used for different things. For example, if we wanted to know the final location of an object, the displacement will tell us where it is relative to where it started. If our object was a car and we wanted to know how much gas it used on its trip, we may care more about the total distance because the car uses gas regardless of the direction. The key here is that in general, these two quantities are different. They happen to be the same whenever the motion is in a straight line or the object does not change direction. If the object doesn't change direction, then it never comes into play, so the distance and displacement should be the same. Otherwise, displacement could be positive, negative, or 0 depending on the motion. The sign of the displacement also does not depend on the initial or final position values alone. For example, if an object starts at minus 50 meters, just meaning it is 50 meters to the left of the origin, and then it ends up minus 20 meters to the left, the displacement is negative 20 minus a negative 50, and this gives us a positive 30 meters. The positive 30 represents the fact that the object moved to the right an amount 30 meters. It is positive despite both the individual positions being negative. But if we were to swap the order, and go in the other direction, now the object is moving to the left and we'll get a minus 30 for our displacement. Let's try to justify why we define displacement to be final minus initial position. We can represent the position of an object as a vector that points from the origin to the location of the object. If we start at one position, x1, and move to another position, x2, we can ask how much we need to change our first position for our object to be at the second position. We'll represent this as the change delta x. Using our rules for adding vectors graphically, we need to draw the vector delta x from the tip of position vector 1 to the tip of position vector 2. Mathematically, this means if we start with our first position, x1, and we change it or move it by some amount delta x, which could represent a negative number by the way, then we arrive at our final position. Hopefully the logic of this equation makes sense. It's like the balance in your checking account after you get paid is the final state, or x2, and how did you get there? Well, you started with some amount of money, maybe zero, maybe more, and then you added a paycheck, which would be your delta x. Now we can just rearrange this equation to solve for delta x and get our equation from before. This is a good exercise for taking a basic equation and trying to make intuitive sense of what it's telling you. We are looking at motion in one dimension for now, but this motion does not have to be horizontal and represented using coordinates on an x-axis. We could also consider motion straight up and down and use delta y as our displacement in the y direction. In general, we can write the displacement using the letter r to represent motion along an axis in an arbitrary direction. Some textbooks use the letter s as well instead of r. Then, if our motion does happen to be horizontal or vertical, we can just replace the r with x or y. This makes it easier to write general equations rather than writing all of the possible options in terms of x, y, and any other axis. Now let's move on to velocity and speed. Specifically, we'll look at average velocity and average speed. Average velocity is the rate at which position changes with time. And since the change in position is displacement, we can write average velocity as displacement over the time interval delta t. So the units are meters per second. As we can see, velocity is a vector and it has the same direction as displacement. The direction does not depend on the first or second position by themselves, but the difference between the two. We can expand delta r over delta t as final minus initial of each quantity. We can also use f and I to represent final minus initial instead of 2 and 1. Now, when we describe an object's motion in some time interval, we don't use the current time on our clock or the date. Instead, we imagine starting a stopwatch the moment the motion starts, or at least the part we're interested in. And even if we look at the later motion of the same object, we could start the stopwatch over again and look at the motion during a different time interval separately. For this reason, the initial time is often set to 0, and doing this makes the change in time delta t equal to the final time. So you'll often see this time interval just written as a single letter t. When you see this in other places in physics, know that we are nearly always talking about a time interval, not the time at a single moment. Also, time always ticks forward, so time and delta t, a time interval, will always be positive. Now, average speed is the total distance over a given time interval. So just as velocity is a vector and depends on displacement, speed is a scalar and depends on distance. And average speed has the same units as velocity, which are meters per second. In the same way that the magnitude of displacement and distance may be equal, in general they may not be equal. The same is true for average velocity and average speed. An object may have moved through a large distance, but if it ends where it started, the displacement is 0. And since average velocity depends on displacement, it is also 0, even though distance and speed may be positive and possibly even very large. The reason average velocity and average speed are not equal is because one is a vector and one is a scalar. If direction changes, these quantities will be different. If the motion is in a straight line, again, direction does not come into play, so speed and magnitude of velocity may be equal. Now we'll look at position and velocity graphs. If we plot position versus time, a point on this graph is the location of an object at a specific time. If the graph then increases with time, or increases left to right, this means the position is increasing. We can also look at two different points on the graph to look how the position has changed within some time interval. This is represented by the slope of this graph, and we already have an equation involving the slope. Slope can be written as the change in the y-axis over the change in the x-axis, which for us is the change in the position x over the change in time. This is our definition for average velocity. It's important to know how to read these graphs because we will see many different graphs in the future and they give us a lot of information. So the first two things you can ask yourself about a graph is, one, what does a point on the graph represent? And two, what does the slope of that graph represent? And then don't confuse the two. Let's look at the simplest case of a position graph where the position is given by a straight horizontal line. The points on a horizontal line do not move up and down, so the position isn't changing with time. So a horizontal line tells you that the value of the y-axis, in this case position, is remaining constant over time. The fact that the line is straight tells you the slope is constant. In this case, the slope remains 0, so the average velocity is 0, which is consistent with an object that isn't moving. Now we can have a straight line that is at an angle. In this case, our straight line has a positive slope. This means the value or position is constantly increasing. A straight negatively sloping line would mean the position is constantly decreasing. In both cases, the lines would be straight, so the slope is constant. It's just now the slope is positive or negative instead of 0. Now let's look at a curved position graph. Here, not only is the position increasing, it seems to be changing faster as time goes on. If we look at the average velocity over a time interval, we draw a straight line through the 2 points. The slope of this line represents the average velocity. Notice the slope is constantly changing, so the average velocity is just that, an average. It's not how fast the object was moving at any given point in time. But what if we want to find how fast an object is moving at a specific time, such as t1 on this graph? To do this, we can imagine bringing the points closer together. The slope of the average velocity line changes, and eventually it approaches the slope of our graph at time t1. It's important to use the word approaches. If we keep going until t2 is equal to t1, our average velocity formula breaks down since we would be dividing by a time interval of 0. To fix this, we use some math called a limit, where we look at the value the slope approaches as we shrink delta t. Now our line only touches the graph at a single point. We can say the slope of the graph at the given point is the slope of this line that only touches at that point. We call a line like this, which only touches at a single point, a tangent line. When our line passed through 2 points, it would be called a secant line. In both cases, the slope of this line represents velocity. Before, it represented average velocity, but the tangent line gives the slope at 1 point, so we'll say this slope represents the instantaneous velocity at that point. Mathematically, you may recognize this as a derivative from calculus. The instantaneous velocity at some point in time is given by the first time derivative of position at that time. We've been looking at the position graph and using the slope to describe the velocity, but we could also draw a velocity graph separately. A constantly increasing position will have a constant positive slope. This gives a velocity graph with a constant positive value, or a straight horizontal line above the x-axis. Now let's look at what happens when the velocity is not constant. This is called acceleration, which we define as the rate at which velocity changes with time. We can define average acceleration in a similar way as average velocity. And looking at the equation, we see the unit should be meters per second, or meters per second squared. We'll look at what it means to have units with seconds squared on bottom shortly. Like average velocity has the same direction as displacement, average acceleration has the same direction as the change in velocity. Again, the direction does not depend on the individual velocity values, but their difference. We will also focus on acceleration that is constant. Acceleration is not always constant, but many types of motion that we experience can be approximated as having constant acceleration. And in this case, the average acceleration and instantaneous acceleration are always the same value, so we tend to just drop the average abbreviation in the subscript. This formula for average acceleration also looks like our formula for slope, but this time the velocity is on the y-axis. On our velocity graph, a point represents the velocity v at a time t, and the slope represents how the velocity is changing, which we now call acceleration. When we are considering constant acceleration, the slope of the velocity graph will remain constant. This means the velocity will always either be a straight horizontal line, or a straight positively sloping line, or negatively sloping line, but never a curved line like we saw for position earlier. We also define the instantaneous acceleration in terms of derivatives from calculus like we did for instantaneous velocity. In this case, acceleration is the first time derivative of velocity, which means it's also the second time derivative of position. Again, we usually just call this acceleration instead of instantaneous acceleration because for most of our cases in intro physics, we look at constant acceleration. I want to look at the units of acceleration and get a better grasp of what acceleration means. Instead of writing the units as meters per second squared, which is simplified, we'll write it as meters per second per second. Now suppose we have an object and it begins with no velocity, and it will accelerate at minus 10 meters per second squared downward, or in the minus y direction. We can write this as minus 10 meters per second per second. Now we can look at how velocity changes each second. After 1 second, the velocity has changed by minus 10 meters per second. So the new velocity is minus 10 meters per second. After another second, the velocity should again change by another minus 10 meters per second. So now the velocity is minus 20 meters per second. And again, after a third second, now the velocity is minus 30 meters per second. So this acceleration tells us that the velocity will change by minus 10 meters per second every time 1 second goes by. But if we think about position, since the object is moving faster during every 1 second time interval, it will move through more and more distance. We started with position graphs and found velocity, and then got acceleration from a velocity graph. But what if we want to go the other direction? If we have an object that begins moving with some initial velocity, and we want to find the final velocity of that object at some later time, we can do this using acceleration. The final velocity can be written as the initial velocity plus however much the velocity changed in some time interval. Graphically, this change in velocity is given by the area under the acceleration graph within this time interval. In this case, the area is a rectangle with a height equal to the acceleration value and a width equal to the time interval delta t. In general, this area can be found mathematically using an integral. An integral is just a way of breaking up an area like this into small pieces and then adding them up. This makes it easier to get the area when it's not as simple as it is here. But notice the integral here looks just like what we think it should be. It's the area, or height, times the time interval. But if we break up the time interval delta t into really small pieces, each piece of time we'll label dt. Then the integral sign looks kind of like an S, which we can imagine stands for sum, where we add up all of these little pieces from the initial time to the final time. The same is true for position and velocity graphs. If we know our initial position and want to find the final position after some amount of time has gone by, we can write the final position as where we started plus how much our position changed. Then this change is given by the area under the velocity graph during this interval of time. And we can again express this as an integral. In the next video, we will focus exclusively on cases of constant acceleration and find equations that allow us to fully describe the motion of objects. These are often called kinematic equations, and we will look at a practical example of constant acceleration called free fall. So that's it for this video, and I'll see you in the next one.